Okay, so 4B today is stationary points again and turning points. There are 3 types of stationary points, and remember that stationary points mean that there is a gradient of 0. We have the minimum turning point. It does say there a local minimum because it may not be the lowest value overall for the whole entire curve, but in that specific area it is the lowest point. And we have a local maximum. And then we did see these briefly last lesson. We have horizontal points of inflection, which while they're not actually turning around, they're not turning like a parabola kind of shape, they are slowly becoming a 0 gradient before they continue to be either all positive or all negative. Okay, so it says that we're going to use a table of values to determine what type of stationary points that we have. There is 2 ways that you can actually do this. When question asks you what nature a stationary point has, one method is going to be use the table of values, which is what we're going to be using today, and there's another method I'll be showing you later on, which is to do with the second derivative. But for today, the tables. Question number 1 says, I want to find the stationary points on a cubic, which is y equals x cubed minus 6x squared plus 9x minus 4, and use the derivative table to determine their nature. Sketch the curve. Okay, so yesterday we learned that if I want to find the stationary points, I have to differentiate and make my derivative equal to 0. So that's what we're going to do first. The derivative y dash is equal to one term at a time. So first of all, the x cubed. We bring the 3 down the front, leave the x, subtract 1 from the power. Then onto the second term, bring the 2 down and multiply it with the minus 6 to become negative 12x. And 9x, we'll keep the 9, the x will disappear, and the constant will disappear. Now I want to find when that derivative is equal to 0. That bird is really loud. Anyway. The derivative was 3x squared minus 12x plus 9, and I want to make that equal to 0, and I'm going to solve it to find the x values. It's a quadratic, but I could factorize a 3 out of all of those terms, which will make it a little bit easier to factorize, so let's do that. 3 out the front of x squared minus 4x plus 3 equals 0. Now that's a monic trinomial, which will factorize to 2 brackets like this. Yes, so the 2 numbers that times give 3 and add to give a minus 4 will be x take away 3 and x take away 1. Using null factor, we then get 2 x values. One is x equals 3 and the other is x is equal to 1. Because we're after points, it's always good at this stage to find the y values that go along with those. So I want the y value for that, and I want the y value for that one as well. Remember to sub that into the starting equation, not your derivative. So subbing 3 into here, you're going to go 3 cubed minus 6 times 3 squared plus 9 times 3 minus 4, and you get? Minus 4. Very good, yeah. And then do the same thing for 1. Excellent, good. So I have 2 turning points. 3, negative 4 is the first one, and the other one is 1, 0. So that was pretty much what we did last lesson. Today we want to take a step further, which is to determine the nature, meaning maximum, minimum, or point of inflection, from a table. So the table will have 3 rows. The top row will be the x values that I'm going to choose. The second row is going to be the gradient, y dash, because I want to see what is happening to the gradient around my stationary points. And then the bottom row is one that we're just going to call the slope, where we're just going to be drawing positive and negative slopes in there, and zeros. Okay, so the 2 points that I have for x were 1 and 3. So we want to have points in between those. So I'm going to leave a gap, and then I'm going to have the 1, leave another gap, have the 3, and then I need 1 on the end. So I'm testing every side of those points. So then I pick values to fit. Let's go something less than 1. I hope 0 is the obvious choice. Between 1 and 3. No, that's above 3.
8.
Okay, and then above 3. Don't make life difficult for yourself. Okay, 4. Nice, easy. You need to sub those values into the gradient. Okay, so each of those we're subbing them into, let's scroll back up so I can see it, into that equation there. Okay, now 2 of them we should be able to do without needing our calculators. We know that we have turning point at 1 and at 3, so the gradients there should be 0. Okay, but grab your calculators for the others. So sub 0 into here. Actually, that's an easier one. 0, 0, 9. That one's a good one. Sub 2 in.
-2 and 8.
-2, good. Sub 4 in. Ben said -2. I think Ashton said something different. 9, good. Thank you, Jess. So the slope row, if it's not the size of the number that's important, it's the positive and negative part that's important. So if 9 is positive, that's going to be sloping uphill. It's -3?
Yeah.
Is it -3? Did anyone else type that in? For the middle one I presume you're talking about?
Yeah. Yeah.
It is -3?
Yeah.
Am I trusting you or are you saying that?
Does it matter? Because it's
It doesn't matter. Still negative. All right. So 0 is going to be here. So flat line is 0. -2 or negative whatever is sloping downhill. 0 again. And a positive 9. Now, although it looks a little bit jumbled in there, what you can see is the positive 0, negative, that is the concave down. That means that that is a maximum. This one here is a maximum turning point. And the 3, the ones on either side of the 3, was a -0, positive gradient. Okay? So that means, therefore, the 3, actually let's start with the 1 first. 1, 0 is a maximum, so max for short. And the 3, -4 is a minimum, or min for short. And I need to draw it. So on the right side, should be drawing, not talking. So I have one of my turning points was 1, 0, which is here. The second turning point was at 3, -4, which I'll put down here. Because you know the maximum minimum part, 1, 0 was a maximum, you can put a little bit of curve there. Just I know that has to curve that way. And the 3, -4 is a minimum, so I know it has to be coming up, which also makes sense based on where those points are located. I could also include a y-intercept on that graph, which will be where? -4. That's looking back to the original equation, where the number on the end was a -4. So let's draw our curve. It'll come up, curve around the maximum, And it's going to come up through that x-axis again, but I think we do not need to find the x-intercept, so I'm not even going to draw it going through there. Okay, that's it. Let's do it again. Question 2. Find any stationary points on the curve f of x equals 6x to the power of 5 minus 20x squared, and distinguish between them. So, like we did before, if I need to find the stationary points, I need to differentiate. This time I'm using f of x notation, so it'll be f dash x for the derivative. Bring the power of 5 down the front and times it with the 6 to get 30x. Subtract 1 from the power will be a 4. For the second term, bring the 2 down, multiply it with the 20, so negative 40x. Subtract 1 from the power would be a power of 1. Then I want to make my derivative equal to 0. So that means that 30, x to the 4 minus 40x is equal to 0. And I solve it to find the x values. To do that, I'm going to have to factorize. So the two terms have a common factor of 10 and x that can come out the front. For the first term, that will leave a 3x cubed. For the second term, 40 divided by 10 is 4, so negative 4, and the x has been taken out the front, equals 0. So using null factor, from the 10x part, I would simply get that x is equal to 0. From this bracket, the bracket though, it's a little bit more complicated. It's 3x cubed minus 4 equals 0, which you want to move the 4 across. 3x cubed equals 4, and x cubed will equal 4 over 3. But then to get the x, I have to cube root that. And that is just not going to be nice if I leave it exact. So at this point, I went to a decimal. Okay, so it didn't specify I had to do exact, so that's fine. I can go to a decimal. The cubed root of 4 over 3, 1.1. I put 1.10, I did 2dp. So you can see I'm operating with two columns there. So this is x value number 1, x value number 2. Remember, I need to find the y values. So straight underneath, y equals and y equals, so that I complete the point. Sub the values back into the original equation. 0 is nice and easy. 0, 0, which means that y is equal to 0. Okay, next one, not quite so nice. Sub in 1.10 into that equation. So you want to tell you what I had? You want me to say?
0.07.
No. You're just guessing. You're not typing things in. Yes. Did Tori type it in?
I just wrote it out.
Oh. So minus 14.54. So let's write them down as coordinates. Turning point. The first one is 0, 0. And the second turning point is 1.10, comma, minus 14.54. Two turning points. Let's determine their nature. And we do that with our table with 3 rows. First row is the x values. Second row, we're testing the slope. We're putting it into the derivative. And the third row is where we draw our slope. So our x values this time, let's put a few columns in here. We have 0 as the smaller value and 1.10 as the second value, and I need gaps in between. So something less than 0, I'm going to use negative 1. Something between 0 and 1.1, just use 1. Nice whole numbers are the best. And something bigger than 1 is 2. So the turning points, the gradient should be 0. So those ones we know straight away. You can check them by subbing them in just to make sure you've done everything correctly. But you can just write those ones down. Next, we need our calculator, and we're subbing these other values into our, I will call it y dash, but it's my f dash x up here, this one. So 30 times minus 1 to the power of 4 minus 40 times negative 1.
70.
Yes. So 70, and then I got minus 10 and 400. So the slope, 70 is positive, so it's going up. 0 means horizontal. Negative 10, negative slope is going down. 0 is horizontal again, and 400 is a positive uphill gradient. And you can see from there, you don't have to do this, but if you like to, you can bring the first turning point out. There's the first one, and then there's the second one. If you're happy looking in the table though, that is fine. So the first turning point is a maximum. Okay, it's the concave down one. So therefore there is a maximum at 0, 0. The second one is a minimum value at 1.10, negative 14.54. This question does not ask us to sketch it. It just asks us to find those stationary points and to work out what type they are, and we have done that. All right, question 3. All good? Question 3. The graph of the cubic f of x equals x cubed plus ax squared plus bx has a stationary point at 2, 2. Girls, find A and B. All right, well, if they're, without having to differentiate anything, I know that there is a point 2, 2 that is on that curve. Correct? There's a point, it says there's a point at 2, 2. Right? So if I'm just going to sub in when x is equal to 2 and y is equal to 2 into just my f of x equation, no derivatives. So that the f of x represents the y value. It will be 2 equals 2 cubed plus a times 2 squared plus b times 2. And I'm going to tidy that up. So that's 2 equals 2 cubed is 8 plus 2 squared is 4, so 4a plus, and b times 2 is better written as 2b. And maybe you can see where I'm heading with this. We're going to end up with some simultaneous equations in this question. So I'm going to try to get one of my pronumerals by itself. So first thing, B is probably easier because it's got the smaller coefficient. First of all, though, move the 8 across. We could collect the 8 up with the 2 there. So that's going to be negative 6. If I subtract that across the other side, equals 4a plus 2b. Can you see there that all of those terms
Going to 2.
are divisible by 2? So let's simplify. So that's going to be minus 3 equals 2a plus b. And so then it's very easy to leave the b and subtract the 2a across the other side. So I have b equals minus 2a minus 3.
Or you can have B equals 2a plus 3. Shove us in.
Yes. They're both minus though, right?
Just leave it B.
You always can be counted on for a joke, Ashton.
But Ashton said.
Or you literally don't.
What did Ashton say?
He said to be or not to be, and then he said just leave it be. So that means he's fine.
Okay. All right. That is only one equation. If I'm hoping to try and solve this for A and B, I need a second equation that has both of those pronumerals in there, and that is going to come from the derivative part. Because I know that I have a stationary point, which means the derivative will be 0 at that point 2, 2. So let's find our derivative. f dash x equals, bring the 3 down, so it becomes 3x squared, plus, don't worry about that a there, bring the 2 down the front, and it will become 2a x to the power of 1. And then differentiating bx, b is just a number, so the b stays, the x disappears. Okay, so that's my derivative. As I said, because it's a stationary point, that means my derivative is going to be equal to 0 when or at the x is equal to 2, because it was at the point 2, 2, and I'm taking the x value from there. I'm not going to take the y value because I'm now talking about the gradient. Okay, so subbing f dash x equals 0 into here and x equals 2 into there, I'm going to get my second equation. Let's do it. So that's 0 equals 3 times 2 squared plus 2a times 2 plus b. That makes 4 times 3 is 12 plus 4a plus b. Ben, do you need to go outside? Then I'd appreciate you stopping talking, please. All right, I can get b by itself again, which will make a nice substitution with the first equation that I have. So let's leave the b and move the other stuff across. So minus 4a minus 12. I'm going to label these equation 1 for the first one I found, equation 2 for the second one. And simultaneous equations time. Sub equation 1 into equation 2. Because they're both b equals, it's just going to be, oh, there's a lot of b's in my sentences, isn't there? Minus 2a minus 3 equals minus 4a, take away 12. And I can solve for a. I'm going to take the smaller a term, which is the negative 4, add it across to the other side. We'll make a positive 2a minus 3 equals negative 12. Subtract, moving the minus 3, I'm going to add it to the other side, which will become a negative 9. And finally divide by 2. So it's minus 4.5. I have found a. Of course, I have to go back and find b. Sub it into whichever equation you like, maybe equation 1. So equation 1 is b equals minus 2a, so it's going to be minus 2 times minus 4.5 minus 3. And that actually comes out as a nice whole number. That's b equals 6. All right, that's it.